For Lab 4, we're going to be determining the equilibrium constant for the formation of a complex ion using spectrophotometric methods. So basically what that means is spectrophotometry uses light, and we're going to use light to determine the concentration of a species that we've created and use that to back calculate to figure out where is our equilibrium at this moment. So the objective of today's lab is to determine the equilibrium constant for the formation of a complex ion, specifically iron thiocyanate. And again, we're going to use spectrophotometry to do so. The reaction itself is iron 3+ ions react with thiocyanate ions to form this iron thiocyanate complex. Equilibrium constant, of course, Kc is equal to the concentration of iron thiocyanate divided by the concentration of iron 3+ times the concentration of thiocyanate, all at equilibrium. The reason we can take advantage of spectrophotometry to do this, or the advantage of this reaction, is iron 3+ ions, when they're dissolved in solution, are a very faint yellow color. The more dilute the iron, the harder it is to see that yellow color. Thiocyanate is colorless, while the complex you're forming is a deep orange or red color. So we can use spectrophotometry, or light, to measure the color absorbance of these species, because we're going to use a faintly yellow sample, we're going to use a colorless sample, and we're going to make a deep red color. The absorption spectrum of the reaction mixture at equilibrium can actually be monitored, and we can use this to determine that concentration of iron thiocyanate. So we will use what we call blank. We will train the instrument to recognize the absorption for the iron complex to subtract out that light yellow color, and then we know whatever absorbance we're getting is only due to our desired product. So some concepts for today's lab: equilibrium constant, complex ion, and ligand. Equilibrium constant, or Kc. Remember, if Kc is a lot bigger than 1, the reaction is product favored. If Kc is a lot smaller than 1, the reaction is reactant favored. If Kc is about 1, the reaction proceeds about halfway. It's neither product nor reactant favored. A complex ion is an ion that is formed in solution by mixing a simple metal salt with a ligand. In this case, we're actually going to mix iron nitrate with thiocyanate and form this iron thiocyanate complex, which we have pictured here. You see what's going on here is that actually we call these ligands, and they coordinate to the iron complex in the center. So we've got your water surrounding your iron, and then your thiocyanate, all coordinating to the iron center. A ligand is a molecular ion that exists on their own but can bind to a metal ion. So thiocyanate, SCN minus, thiocyanate can absolutely exist on its own, but it can also bind to that metal ion. So it's that whole opposites attract thing. We're going to use Beer's law. Beer's law is we can take advantage of when we're doing spectrophotometry. Beer's law states A equals epsilon BC. A is your absorbance at a particular wavelength. Epsilon is your molar extinction coefficient, with units liters per mole centimeter. Epsilon, or your molar extinction coefficient, measures how strongly a species absorbs light at a specific wavelength. B is your cuvette path length, typically 1 centimeter. To actually measure these samples, we put the liquid into a cuvette, and I'll show you actual photographs of this in just a minute. We put this into a cuvette, and we pass a light through here, and we see how much light goes through here. So we have to measure the distance the light can pass through. It goes into a cuvette, so we measure the cuvette path length, and typically that's 1 centimeter. C is your concentration of your absorbing species. In this case, we're going to look at our iron thiocyanate. So in here, we would have our iron thiocyanate absorbing the light that's traveling through that cuvette. A spectrum is collected on a spectrophotometer, and absorbance is measured at what we call your analytical wavelength, or your lambda max. So when we actually do this, we're going to run the spectrum, and we're going to see some kind of peak, and it will go back down. We're going to find that peak. That peak is at lambda max. or maximum wavelength. We want to use your maximum wavelength, your analytical wavelengths, because we want to know where this species best absorbs. Where it absorbs the most will give us the most accurate data. So looking back at the electromagnetic spectrum, I know it's been a while since you guys looked at this, but we're talking here in our visible region. Okay, so about 400 to 750 nanometers is our visible region. Remember, as we go from left to right on the electromagnetic spectrum is we're going to longer and longer wavelengths, but that's lower energy and frequency. As we go from right to left, we're going to shorter wavelengths, higher energies, and higher frequencies. In today's lab, we're specifically looking within our visible spectrum because we're going to be monitoring actual colored species. So we're going to be dealing here between 400 and 750 nanometers. So our lambda max that we're measuring should be somewhere between 400 and 750 nanometers. So also just kind of reminders for what light means. Remember when visible light comes in, if it hits a surface that's white, it reflects all of that light back. So if you see like a light bulb is actually reflecting every possible color back at your eyeball at the exact same time. If you see something that's black, black absorbs all colors of light. So if you see something black, it's because it's absorbing all color and all that's left is nothing. If you see something that's yellow, it's absorbing all color, it's reflecting yellow back at your eye. So again, when we have white light coming in, so like from the sun, it's actually white light. And we're getting all of those wavelengths, red, orange, yellow, green, blue, indigo, violet, are all coming in to what we're seeing. So when you see something that looks white, it's actually every single color reflecting at you. The spectrophotometer is going to monitor all of those wavelengths and see where is the species absorbing light. And it's going to give us that relationship. Absorbance is related to epsilon, molar extinction coefficient, times your path length, times your concentration of your species. So your absorbance is proportional to your concentration. The higher the concentration, the higher the absorbance of that species will be. Lower concentration, lower absorbance. We'll be able to test and measure how high is that, what kind of concentrations do we have in an unknown species or at equilibrium if we can measure the absorbance. Spectrophotometers work as follows. We've got your sample cuvette in the middle, and this is where you're going to have your iron thiocyanate complex. We've got a light source that's going to pass white light, and it's going to pass it through a slit. The slit is going to move. When we first figure out your full spectrum to figure out your analytical wavelength, that's going to run the entire spectrum. Then we're going to go back and we're going to set it to measure at one specific wavelength. It's going to set that slit up to measure at our maximum or our analytical wavelength. That wavelength is going to come in and it's going to hit our sample, pass through our sample, and whatever light is absorbed is going to go out into the diffraction grating and then hit the camera. That will then tell us how much light we actually have absorbing in our species, because it measures the transmittance so it knows how much went through, it knows how much it put in, so it can calculate our absorbance. If it knows how much light went in and it knows how much light came out, it will know how much light was absorbed by your sample as well. So let's go ahead and work an example. A solution of cobalt NH3 2+, so this is a cobalt ammonia complex, was prepared by mixing cobalt 2+, which had a concentration of 0.1 molar, and ammonia, which had an initial concentration of 2 molar. The complex has a measured absorbance of 0.561, epsilon 90 molar per centimeter, and path length of 1 centimeter. What's the equilibrium constant for this reaction? So what they did here originally was they mixed 0.1 molar cobalt with 2 molar ammonia. You see our ammonia is in a huge excess compared to the cobalt. We're going to do something similar in this lab. and they formed this cobalt ammonia complex. Step 1 is determining your molar extinction coefficient. You're going to have to do this as well. First thing to do is determine the concentrations of solutions after dilutions, so after mixing in part 1. In part 1, you're going to take 3 different things and you're going to mix them together. You're going to have iron, thiocyanate, and nitric acid. I give you all of the volumes that you're going to use, and I give you their initial concentrations. You need to calculate their concentrations after mixing, because you're going to use M1V1 equals M2V2 to do that calculation, but you need that value, okay? Here we saw ammonia was in a large excess. In your reaction, you're going to have thiocyanate in a large excess. This will make, in this reaction, it makes cobalt the limiting reactant. In your reaction, it makes your iron your limiting reactant. How does this information help us, though? Well, the reason this information helps us, if I know, for example, for this example, cobalt is my limiting reactant and ammonia is in large excess. This is an equilibrium, yes, but if I know cobalt is limiting and ammonia is in large excess, then I can assume that all of my cobalt has been used up to form the complex. That also means I can use a stoichiometric relationships to say, okay, if all my cobalt was used up, I know I have this many moles of cobalt after I figure out my new concentrations, my new volume of cobalt that went, my volume of cobalt that went in and my new concentration. I can figure out my moles of cobalt. I can then stoichiometrically convert that to my moles of my complex. And then that to the concentration of my complex. I know my absorbance. I measured on a spectrophotometer. So I've got A equals epsilon BC. I measured A. I can calculate C, and B is 1 centimeter. Now I can determine my molar extinction coefficient for this reaction. So epsilon equals A over BC. You need to do this graphically. So what I have here is I have my new concentrations of my complex. Again, I got my concentration of my complex based on my moles of my complex, based on my moles of CO2, or sorry, my moles of CO, based on my dilutions. Okay? So I've got my concentration of my complex, and I've got my absorbance of my complex. Keyword here, don't forget your 0,0 measurement. It's not often we have you go through the origin, but in this reaction you do. We want to make sure you include that 0,0 point. A concentration of 0 should have an absorbance of 0. Go ahead and plot that, and you're going to get a plot like this. When you plot this, what we've done here is we have your absorbance over here, we have your concentration here. We're trying to get epsilon. When you know epsilon equals A over BC, we know this, your slope is rise over run. Therefore, my slope in here that value right there without the variables, that 35.159 is my epsilon value. So epsilon for this reaction is equal to 35.159 molar to the minus 1, centimeter to the minus 1. Now I have my molar absorptivity coefficient. Now, in part 2, I can create a true equilibrium where my concentration of cobalt and ammonia are a lot closer to each other, create an actual equilibrium here, use my molar extinction coefficient and my absorbance to back calculate to the concentration of my complex. You know the molar absorptivity coefficient of this complex, we can go ahead and use that information to calculate the equilibrium constant of a true equilibrium for this reaction. So we're going to recreate an equilibrium, but in this case, we're not going to flood the system as strongly with excess ammonia. Instead, we're going to have these to create a true equilibrium within the system. So here, a solution of the cobalt ammonium complex was prepared by mixing 10 mils of a cobalt solution, originally at 0.2 molar, and 10 mils of an ammonia solution, originally at 4 molar. The complex had a measured absorbance of 0.561. Epsilon was found to be 35.2 per molar per centimeter based on the previous graph, and the path length was 1 centimeter. What is the equilibrium constant for this reaction? Well, we need to determine the concentration of our equilibrium. So we know at equilibrium, we have an absorption here of 0.561. We know our molar absorptivity coefficient is 35.2 per molar per centimeter, and our path length is 1 centimeter. So again, this is just rearranging Beer's law, where A equals epsilon BC. This is C here. We solve for this and we find at equilibrium, our complex concentration was found to be 1.59 times 10 to the minus 2 molar. So we know that that's the concentration of our complex at equilibrium. Now that we have our concentration at equilibrium, we can back calculate to figure out the concentrations of our other species. You do need to set up an ice table to do so. So your ice table, we've got your initial change in equilibrium, we've got your cobalt 2+, your ammonia, and your complex. We originally started with 10 mils of cobalt 2+ at a 0.2 molar concentration and mixed this with 10 mils of ammonia at a 4 molar concentration. I used M1V1 equals M2V2 to figure out my new concentrations of my cobalt and ammonia. So my cobalt, once mixed, had a concentration of 0.1 molar. My ammonia, once mixed, had a concentration of 2 molar. Our change, minus x plus x, and at equilibrium, we know we will have 0.1 molar minus x, 2 molar minus x, and x for for our complex of cobalt ammonia. Substitute the values you just calculated into your ice table. So again, we found this from M1V1 equals M2V2. Same for this. And initially, we don't have any of our complex present. We found at equilibrium, we had 0.159 times 10 to the minus 2nd molar of our complex present, which means that this value is equal to x. We know it was plus x here. We know this was minus 6x because we have a 6 in front here, and we know this was minus x for the changes. So therefore, at equilibrium, I took 0.1 molar for my cobalt 2+ species and subtracted 1.59 times 10 to the minus 2nd molar, giving me an equilibrium concentration of 8.41 times 10 to the 2nd molar for my cobalt 2+. For ammonia, I took 2 molar minus 6 times 1.59 times 10 to the minus 2nd molar to give me an equilibrium concentration of 1.90 molar for ammonia. Step 5, determine your Kc. So I plug all of this into my equilibrium expression. Remember, products over reactants. So I've got my concentration of my complex here, my concentration of my cobalt here, and my concentration of my ammonia here, all at equilibrium. Calculate that through, and I get an equilibrium constant expression, or equilibrium constant of 4.02 times 10 to the minus 3rd. Remember, too, don't forget, the coefficient out here becomes a superscript in your equilibrium expression. How are you going to actually do this lab? Well, we have this lab split up into 2 parts, parts 1 and 2. It's very, very important that you keep it straight what part you're doing so you're using the right solutions in which part. When you get to part 1, you're going to have 3 graduated pipettes. Please label all 3 pipettes. You want one for each solution. You have an iron solution, a thiocyanate solution, and a nitric acid solution. I say label them because we don't want you to get them mixed up. Cross-contamination in this lab will completely ruin your results. So please label them so that you keep them straight throughout the entire period. For part 1, you will prepare 5 different solutions labeled A through E. Some key things here. DI water is not to be used. Okay, you can use DI water for cleaning, but you should not be adding DI water to anything. Everything is prepared in a nitric acid solution. You do need to be careful. Nitric acid is an acid. It's rather corrosive. Okay, it can oxidize things pretty nicely, and you don't want that to be happening. So use caution, but you do need to use nitric acid as your solvent throughout this entire lab. There's a reason behind that we're not going to get into in a Gen Chem level. It deals with activities of solutions and such, but it is required to do this lab in nitric acid to actually get it to work properly. You will be using 0.2 molar iron nitrate and a 9 times 10 to the minus 4th molar thiocyanate concentration, thiocyanate solution concentration for this part. Please make sure you have these correct. So 0.2 molar iron nitrate and 9 times 10 to the minus 4th molar potassium thiocyanate are used for part 1 only. You also have, again, 0.5 molar nitric acid. All of your solutions, including these, have been prepared in nitric acid. You're going to measure the absorbance of the solutions A through D from 400 to 700 nanometers. Solution E is just your blank or reference. You'll note in solution E, you've only added in iron and nitric acid. So solution E is what you're using to subtract out that yellow coloring due to the iron itself, the faint coloring that iron provides in solution. Measure the absorbance of the solutions A through D from 400 to 700 nanometers and record lambda max and the absorbance at your analytical wavelength. Dispose of the solutions A through D and any remaining part 1 solutions need to be disposed of. We don't want you to mix them up with your part 2 solutions. Please dispose of all solutions from part 1 prior to starting part 2. Only thing you should be keeping is solution E, which is your blank, just in case you need it. So you can keep solution E around, but everything else should be disposed of prior to start of part 2. So again, the concentrations from part 1 and part 2 are different intentionally. In part 1, we have an iron nitrate solution of 0.2 molar, a potassium thionate solution of 9 times 10 to the minus 4th molar, and a nitric acid solution of 0.5 molar. In part 2, you're not adding additional nitric to anything, but we do our iron nitrate solution in part 2 is 0.01 molar, and our thiocyanate concentration in part 2 is 0.0011 molar. The reason you have to keep these separate is because these concentrations are so different. In part 1, you note, if you look at the difference, 0.2 molar iron to 9 times 10 to the minus 4th molar iron potassium thiocyanate. We are flooding your system with iron. We are adding tons and tons of extra iron. That means that iron is your excess reactant. Thiocyanate is your limiting reactant here. So you can use your thiocyanate concentration to stoichiometrically convert to figure out the concentration of your complex from part 1 to do your graph. In part 2, these are a lot closer in concentrations. So part 2, we're creating a true equilibrium. It is vital that you keep these separated, okay? Follow the table in your handout, which is posted on D2L to prepare the solutions. Measure the absorbance at lambda max for every solution in parts 1 and 2. You're going to carefully clean all beakers and pipettes in between your steps to avoid cross-contamination, especially between parts 1 and 2. Please make sure everything's very clean and separated between parts 1 and 2. For the LabQuest, you guys are going to be using LabQuest for in this lab, and you'll be using spectrophotometers for the first time. So, LabQuest, pictured here, we will have this mostly set up before you come. But for the parts you do have to set up, here's your LabQuest and your spectrophotometer. On your LabQuest, go ahead and click File and select New. This will reset your spectrophotometer. It's going to pop up a box like this, and it's going to tell you when warm-up is complete, and then you can go ahead and place a blank cuvette in the device and click Finish Calibration. When it says dark sample, it is no cuvette in the sample. The spectrophotometer, it's hard to see in the photo, but this has your cuvette goes in this box right here. This is actually open to air. So when it's taking a dark sample, excuse me, what it's doing is it's subtracting light out from the room. So when it says dark sample, no cuvette at all. It needs to subtract out all the light from the room so it can give you a true reading. You have to put your sample in. This is what a blank cuvette looks like. This is a cuvette with just some food coloring, but you're going to place your cuvette into this system. It's hard to tell in the photos here, but the cuvette has two different types of sides to it. It has a clear side, and it has a ridge side. You want to position this so that the clear side is following this arrow. Okay, it will make a difference on your results if you do not place the cuvette in here properly. So the path follows through this little arrow on the cuvette itself, on the spectrophotometer itself, and it shows you which path that light takes. You need to place the cuvette in so that the clear sides follow that path of light. This is what it looks like when it's analyzing, and it gives you this nice, pretty rainbow behind the scenes. You're going to place your first sample in your spectrophotometer and hit the green play button. Wait about 10 seconds and hit the red stop square button. Where the green button is here, once you hit play, it's going to turn, there's going to be a red square button there that means stop. So let it run for about 10 seconds and click stop. It's going to pop up a screen that looks like this. This is your full spectrum. So this is where it analyzes the light, and you're going to have to find your lambda max. You can use the stylus for LabQuest and find where do you have the maximum wavelength here. If you read on the spectrophotometer, it's going to show you absorbance here versus wavelength here. You can use these buttons here to scroll back and forth and find when is your absorbance at a maximum. Record this absorbance and this wavelength. So again, determine your maximum absorption using your stylus. Make sure you record these things, okay? From here, you're going to want to find this max wavelength for the first sample you run. You then want to record all absorbance at that same wavelength. So it may show you a max absorbance at, say, here it says 496.6 nanometers. The next sample you run may say 495.7 nanometers is your max. That's not a problem. Still set every graph after this to 496.6 nanometers. You want to read every sample after this at the exact same wavelength. So record both those values. Okay, so tips for this lab. Pre-label your pipettes, one for each solution, do not mix them up. Check your pipette pump. A strong seal between the pipette and pipette pump will not allow the pipette to wiggle. But please do not jam the pipette pump onto the top of the pipette because you can break it. Use slight pressure to form an airtight seal. Record the exact concentration of the stock solution from the bottle. You need this in your calculations. Label any containers you use. Confirm the solution you're using for part 1 and part 2 are correct. While making the solutions, work on one part at a time and be careful to avoid cross-contamination. Normally we tell you guys to multitask and do as much as, think about working multiple systems up at once. In this lab, no. Do not multitask it. Work one system at a time. Prepare and analyze the solution starting with the most dilute or lightest color, beaker A to beaker B to beaker C to beaker D. So you're going to do lightest color to darkest color. For waste, during the experiment, you can place any waste you have in your temporary waste beaker, your 600 ml plastic beaker. Please don't use glass beakers for your waste beakers. At the end of lab, dispose of the waste in a heavy metal waste container located in the hood. Rinse the beaker with a small amount of tap water and place this in the waste bottle after you dispose of solutions, and after that, everything can be rinsed in the sink as normal.